As our world warms, global sea levels are rising, and the coasts as we know them are changing. More than half of the world's population lives within 40 miles, 60 kilometers, of the coast, where fertile land, port access, and recreation abound. In the U.S. alone, roughly 3.7 million people live within a few feet of high tide. Coastal development has boomed in the last 50 years. This growth at the coasts has occurred without regard to rising seas. But as tides and storm surges encroach inland, and coastal land sinks or subsides, the people and environment of the coastal zone face a wide range of impacts. Changes in sea level are nothing new. Global sea level has fluctuated throughout Earth's history because of changes in land and sea topography, growth or melting of polar ice caps, fluctuations in seawater density, and other factors. Over the roughly 2,000 years from 0 AD to the 20th century, sea level changed relatively little. But in the last 100 years or so, average global sea levels rose dramatically. Researchers used two different measurements of sea level. Relative sea level is the height of the ocean relative to the land elevation at a particular location. Absolute sea level measures the height of the ocean surface above the center of the Earth. In recent years, the rate of sea level rise appears to have accelerated. When averaged over all the world's oceans, using mainly tide gauge measurements, absolute sea level has increased at an average rate of 0.06 inches, 0.15 centimeters, per year from 1870 to 2008. From 1993 to 2008, using satellite altimetry data, average sea level rose roughly twice as fast as the long-term trend, at a rate of about 0.12 inches, 0.3 centimeters, per year. Many processes contribute to changing sea level, and several of these are associated with climate variability and change. They include thermal expansion of ocean water. When water warms, it takes up more space. Inputs of water to the ocean from melting glaciers, ice caps, and ice sheets. Modifications in terrestrial water storage from processes like groundwater extraction. Shift in the land caused by, for example, sediment compaction, erosion, or land lifting when heavy glaciers melt. These cause local or regional sea level changes. Ocean currents also influence a coast's sea level by pushing water toward the land or pulling it away. For example, changes in the Florida Current and the Gulf Stream transport are known to affect coastal water levels. Currents also have normal seasonal and decadal oscillations in response to long-term variations in the global wind fields and climate oscillations. To understand sea level change, researchers compare multiple global datasets taken over several decades. They use various tools, including satellites that measure the topography of the ocean, Earth's gravity field, sea surface temperature, ice sheets, ocean salinity, and more. Since 1993, scientists have relied on a series of records from the TOPEX Poseidon, JASON-1, and JASON-2 satellite missions to construct a global and regional sea level trend composite. Tide gauges, electronic sensors that measure and record sea level height, are another important tool. Gauges are preferably co-located with continuous GPS systems. A global array of 3,000 drifting profiling floats, called Argo floats, measure the temperature and salinity of the upper ocean. Historical records and radiocarbon dating of seafloor sediments and corals offer important clues about past sea levels. This data informs our understanding of present and future sea heights. Climate models, satellite data, and hydrographic observations all demonstrate that, while absolute sea level has increased steadily, relative sea level is not rising uniformly everywhere. This figure reflects the spatial variability of global sea level trends from satellite altimeter data. In the United States, relative sea levels have risen unevenly along the coasts over the past 50 years. On the mid-Atlantic coast and parts of the Gulf Coast, sea levels rose by as much as 8 inches, 20 centimeters. In Alaska and the Pacific Northwest, tectonic plates lift the land up faster than the sea is rising, so relative sea level has fallen in this region. Other geologic processes can also impact sea level. For example, post-glacial rebound causes continental uplift, and sediment deposits in large river deltas cause continental sinking. About 90% of the warming the Earth has experienced has been absorbed by the oceans, causing thermal expansion. Thermal expansion and the melting of glaciers and small ice caps caused most of the 20th century's sea level rise. But Earth has nearly 160,000 glaciers, each one capable of responding in its own way to climate change. While nearly all glaciated regions on Earth are showing signs of ice loss, forecasting how glaciers will contribute to sea level in the coming century is a challenging task. The Antarctic ice sheet extends more than 5 million square miles, 14 million square kilometers, while the Greenland ice sheet spreads over about 656,000 square miles, 1.7 million square kilometers. Researchers can now measure average rates of snowfall and ice flow from the large ice sheets, but they are still working to understand how, where, when, and how much the ice sheets will melt. Changes in these large ice sheets are critical for forecasting sea level rise. Since its launch in January 2003, the IceSat satellite has been measuring the ice sheet's changing thickness. This data visualization illustrates changes in elevation over the Greenland ice sheet between 2003 and 2006. Projected higher global air temperatures are expected to cause increased melting of glaciers and ice caps and will lead to higher ocean water temperatures that will further raise sea levels. The Intergovernmental Panel on Climate Change, IPCC, produces the most robust reports on climate change, which are summaries of thousands of peer-reviewed studies. In their 2007 report, the IPCC estimated that the global average sea level will rise by about 9 to 20 inches, 22 to 50 centimeters. By 2100, relative to 1980 to 1999, under a range of greenhouse gas emissions scenarios. It is important to note that these estimates assumed that melting from Greenland and Antarctica would continue at the same rates as observed from 1993 to 2003. However, new research suggests that the IPCC predictions may be too low and that sea level rise could be closer to 3 feet, 1 meter. One unknown is what will happen in the coming years to the planet's major ice sheets. Meltwater contributions from Greenland and Antarctica have increased in recent years, which could also make the IPCC's projections too low. Higher sea levels directly impact coastal areas, which are the most densely populated and economically active land areas on Earth. Infrastructure, such as ports and harbors, industry, and an extensive built environment, are all concentrated in coastal regions. Even a small amount of sea level rise can produce major changes for coasts. In low-lying areas, 1.5 feet of vertical rise, 0.5 meters, can cause inundation far from the present shoreline. This image illustrates how Charleston, South Carolina, would be impacted by that magnitude of sea level rise. Impacts of rising sea levels will be felt most acutely through changes in the intensity and frequency of extreme events and from the combined effects of high spring tides, storm surges, surface waves, and flooding rivers. In some areas, projections of sea level rise mean tidal flooding that was once an occasional nuisance can become a frequent hazard to residents and their property. In this image from NOAA's Sea Level Rise and Coastal Flooding Impacts viewer, the red color indicates shallow coastal flooding areas. The graph shows predictions of changes in the frequency and duration of current coastal flood events for half-meter and 1-meter sea level rise scenarios compared to today's conditions. More than 200 million people around the globe are already vulnerable to coastal flooding. rising population and migration could increase this number to 800 million by the 2080s. This map highlights regions that are most vulnerable to coastal flooding. These projections of people at risk are based on a scenario for the 2080s that assumes a global sea level rise estimate of 18 inches, 45 centimeters. The coasts support important ecosystems that are sensitive to sea levels and other changes. Rising sea levels cause wetland loss, erosion of soft ground, saltwater intrusion, rising water tables, and poor drainage. Coastal infrastructure impedes ecosystems' ability to adapt to rising sea levels. For example, seawalls and jetties make it difficult for mudflats and beaches to migrate inland as they have during past periods of sea level rise. Uncertainty about future emissions of greenhouse gases and the associated climate response make it difficult to estimate the timescales, magnitude, and rates of future sea level rise. Because we don't know the details of how sea level rise will play out in the future, and it is unclear which strategies people will use to deal with changing sea levels, the actual consequences of sea level rise remain uncertain. The two potential responses to sea level rise are mitigation and adaptation. To be most effective, mitigating or reducing greenhouse gas emissions should occur on a global scale, but individuals can start in their homes and communities. Adaptation happens locally or nationally. The IPCC offers 3 approaches to adapting to relative sea level rise: planned retreat, accommodation, and protection. With a planned retreat, humans exit the coast and let natural systems respond without interference. Sea level rise is already forcing some island populations to consider moving to higher ground. The president of Kiribati, a low-lying Pacific island nation threatened by rising seas, is negotiating a land purchase in Fiji to help secure a future for his people. With accommodation, humans don't interfere with natural systems, but instead adjust how they inhabit the coastal zone. Stilted homes are one example of implementing this strategy. The protection strategy relies on soft or hard engineering, like the storm wall pictured here. East Asia and Europe have the most developed and extensive artificial protective systems. Adaptation can mean both adjusting to the negative effects of climate change as well as taking advantage of any positive consequences of change. Adaptation will require action from federal, state, tribal, and local governments, the private sector, non-governmental organizations, and community groups. Planners and policymakers will need to consider a range of possibilities, since the risk of global mean sea level rising by more than 3 feet, 1 meter, by 2100 cannot be excluded. Each nation's experience in managing and protecting its inhabitants, resources, and infrastructure has been based on a relatively stable historic climate. But adaptation to climate change requires an appreciation of possible conditions that lie outside our current experience. In the short term, adaptation actions that can be most easily implemented are low-cost strategies with win-win outcomes, ones that offer immediate benefits and/or reverse poor policies and practices. Often, adaptations make ecological and human structural systems more resilient and healthy. Decision-makers should also consider the relationship between adaptive actions and mitigation. Adaptive actions that increase greenhouse gas emissions should be evaluated carefully to ensure that their benefits outweigh the risks. Planners and decision-makers need long-term forecasts of global sea level rise and information on short-term variability and long-term sea level change on regional and local scales. Perhaps more importantly, they need to know how future sea levels will affect their community and their way of life. Researchers are working to identify and quantify the causes contributing to sea level change and to develop better models with more reliable predictions.